and spinning at a high speed. Okay, so if we have a wheel, it's spinning around the center point, it's rotating this way at 5,000–10,000 RPM. And essentially the first style is what's first in your sheet. We basically take a wall. So let's talk, we're launching a ball right now. We're launching something round. We take a wall and we go in an arc. It could be 90 degrees. 90 degrees is pretty common. It could be more, it could be a little less, right? 45 is also fairly common. But basically it's a fixed distance around the surface of the wheel, right? And it's typically a little bit less than the size of your game piece. And basically you just shove the game piece in one end. You get this up to speed, right? You store a bunch of energy in the wheel. You shove the game piece in one end. Your wheel's made out of some grippy material. It grabs the game piece and chucks it through there with quite a bit of force, right? And in doing that, the wheel slows down, but it doesn't slow down enough that it just slows down to the point where the game piece is still moving pretty fast. Okay. So, and then that's where your energy comes from, is the wheel slowing down. So the big thing about this is that it only works with round game pieces. Okay. Now it doesn't have to be a ball. We used these in 2013 for frisbees, right? Frisbees are round. You just got to contact it on the edge and roll it through. Right, so you just have to roll on the edge of the frisbee and go through a curved wall. So basically it has to be a game piece that's round in one axis, right? It works best with balls, but you can do it with other things too. So we'll come back to this one. But the other way of doing this, well, there's actually two more ways, and I just kind of lumped them into one category. So that's kind of an arc. I call it a radial shooter. It's kind of a weird name. I don't really like the use of the word radial, but that's what I call it, and there's not really a good name for it. Some people call it an arc shooter. I don't like that name either. But basically, that follows a curve, okay? Another version of that that's very, very similar is you use one wheel. I'm drawing it smaller for space. You have a wall. Typically, you can have one wheel. Typically, you've got two or three. Right, and you've got a fixed wall over here. You push a game piece through there, it rolls its way through there, and comes out the other side with quite a bit of speed. Now, why are we rolling the game piece? Can anybody guess why we're rolling it? What?
I didn't say anything.
Anybody want to take a guess at why we're rolling the game piece? Well, yeah. Yes. That wasn't what I had in mind, but yes, you are correct. Why would we want to roll the game piece when we're accelerating it? I know you have you know it. You need to just say it.
Why do I have to say it? I know it, but I want someone else to know it.
Right, why don't you just spit it out there? I don't think anybody else knows.
Because you want it to spin.
Right, because you want it to spin. So flying objects that are spinning fly a lot more stably than objects that aren't spinning, right? So if you throw like a knuckleball, right, it doesn't spin and it flies weird, right? But if you throw a ball normally where it rolls off your fingers, it's got some backspin or side spin depending on how you throw it, and it flies a lot more stably. So typically when we're launching something, we want it to spin pretty aggressively so that it flies in a more predictable fashion. In addition to that, it's not uncommon for there to become some sort of backboard on whatever we're launching into, and typically top spin or backspin, usually backspin, but sometimes top spin is advantageous. Typically backspin means that if you hit the backboard, the spin will deflect the ball down or to the side, or whatever the situation is. You know, in the year we were doing basketball, they were 8-inch foam basketballs, and basically you'd use a launcher like this or the other one, put a crap ton of spin on it. I mean, they have a lot of spin. When you've got a wheel it's rotating basically at the same rate that it's moving, and it's moving fast. So it's got a lot of spin on it, but that's a good thing. And so basically what teams would do is they wouldn't even aim for the hoop, right? They would just aim for the backboard. It's spinning so fast it would hit the backboard, it would shoot straight down and go right at the hoop. So you just gotta hit it in the middle of the backboard, like you just beam it straight at the backboard and it would go straight down into the hoop in most cases. So it's a whole lot easier to do that than it is to kind of lob something up and in, which is why in 2017 with the fuel, the little wiffle balls, most of those teams were hitting kind of there was like a cone and you were trying to launch into this cone. Most of the teams were hitting the back of the cone, but the backspin was sending them into the actual goal itself. So that's why spin is good. It helps the game piece go into the goal where you're aiming, and it helps it fly more stably. Wiffle balls were kind of a weird exception to that because spin in a wiffle ball does some weird stuff. They're designed to do that, but it was just an extra thing to consider. But with a round ball, it tends to just add a lot of stability in flight. So, all right, so there's another style though, right? We don't have to have a wall, okay? Wall adds spin, you don't have to have a wall. You can add another wheel over here, okay? Well, okay, just that other one that I showed you with the wall, you also have to use a round game piece because it's rolling, okay? This, basically, you can put whatever through this you want. This is how football pitching machines work. They've basically got two wheels. They actually angle the wheels so that it spins the ball in the opposite direction. We've never had to deal with footballs in first. Everybody's hoping that we will, but I'm also dreading because dealing with football's gonna be a pain in the butt, but everybody wants to do it. Yeah.
Football's on the moon.
Football's on the moon. We're actually on an extrasolar planet this year.
Oh, okay.
And I think we missed the deadline for naming too. I don't think I can do that right now. Anyways, so this is an option too, right? Two opposing wheels. Occasionally teams will try to slow one down and speed one up so that you get some spin. It doesn't work very well, but it does cause some spin. In my opinion, it makes the flight path even harder to predict because if the game piece is slipping more on one side than the other, it's just, you're out of luck. But this is how teams who were launching cubes this year were doing it in a lot of cases. They were using two, maybe 4 wheels, right? And they would just shove the cube in and it would chuck it up. And obviously it's a cube, so spin doesn't help you a whole lot. You don't need it to spin. You don't really want it to spin. You're not launching it that far. You're just kind of lobbing it up. So that this is a perfectly acceptable application and really the only option using spinning wheels. All right, so we're going to come back to this. We're going to talk about pros and cons. Pros and cons for this stuff is really important and fairly complicated, so we'll get back to this. All right, so that was kinetic energy, storing energy, which is going to be imparted to the game piece in the form of kinetic energy. Now we're going to talk about potential energy, basically springs. You could use a weight, but most people don't use weights because we're constrained for weights. You'd use a spring. Fairly obvious one. Catapult, right? You stick game piece, you cock it back, and you let it go. Fairly simple. You can launch pretty much whatever you want. You can launch other robots, you can launch balls, you can launch cubes, you can do pretty much whatever you want. Students. You can launch students.
Teach me.
No. Can't, no.
But you can?
No. It just doesn't work. There's no way to launch a saw blade with it. Just can't. I'm sorry.
You have to use this one.
Yeah, we gotta use that one.
What's that?
The one with like the 3 wheels and the wall next to it.
Oh, right. Okay. Catapults are the difficulty with spinning wheels is getting that transferred to the game piece. The distance between the wall, you need to squeeze the game piece, but how much to squeeze the game piece is a bit tricky. How fast should the wheel be spinning? What material should the wheel be made out of? Do you want a smooth wall? Do you want a foam wall? that was our big issue in 2017 for the students that were around. Basically the reason that our shooters never worked was because we were using foam on our wall. That was literally the only thing we had to do was put a big thick piece of foam on the wall, and they probably would have worked great. Fun fact. But yeah, I mean that was what 3010 did. They were like, we couldn't get our shooter to work, and we added foam, and it just worked. So you live, you learn. Anyways, but in a lot of cases, you don't want foam because it screws with the clearance and it doesn't act as consistently because the foam wears out over time, and it's the whole thing. Anyways, getting the contacts between the wheel and the game piece and making that work the way you want it to is the hard part with a spinning wheel shooter. Okay, it takes some tweaking, takes some tuning. It's not that easy. Catapult doesn't have any of that. I mean, if the arm is moving, the game piece is moving, right? And it's really just a question of where do you start, where do you stop on your catapult, how long is the arm, and how much spring force do you have, right? Length of the arm really doesn't make a whole lot of difference. You just make it however long you want. If it's shorter, you need more spring force, and you need a more aggressive acceleration to get to a certain speed. If your arm is longer, it can move slower, and you get the same game piece speed, right? It's just kind of a weird game you're playing there. So mechanically speaking, in terms of trial and error and stuff, catapults are simpler. They're easier to do. However, the whole, I want to bring something back that's probably going to take a lot of torque, right? You might have several hundred pounds of spring force depending on what you're launching. You're going to bring that back, you got to hold it in place and then release it all of a sudden with no resistance. That's a little harder to do mechanically than it might seem. There are really kind of advanced, really elegant ways of doing it. There are some kind of cheaty ways of doing it. You can also, in certain cases, use pneumatic cylinders to actuate a catapult. Now, First specifically designs the majority of pneumatics rules to prevent this from being possible. Like, half of the pneumatic rules are actually in place literally just to stop you from launching things with pneumatics. And it's a safety concern. I mean, that's why they're doing it, because, you know, pneumatics that just slam out, you know, with a lot of force can blow themselves up and send pieces through people's heads, and I don't know, but they're dangerous. So they don't want a bunch of high school people running around, you know, basically making pneumatic cannons and then driving them and pointing them at things, right? That's not really what they want. So it's very, very difficult to get a pneumatic catapult / launcher to work well, because the big issue is you just can't get enough airflow rate into your cylinder to do it. And we're operating on fairly low pressures as well. So the issue is flow rate. You almost always have to use like 4 cylinders. You can't use 1, you can't use 2, you gotta use a bunch of them that are smaller in diameter, and you gotta use a bunch of valves. You gotta basically do a bunch of stuff in parallel, and it adds a bunch of weight and adds a bunch of complexity. It makes your mechanism costly. So catapults, pretty simple to get working. There's some mechanical issues that you've got to be able to solve, but they're surmountable. They're also very accurate. I would say they're probably the most accurate shooter we're going to talk about. It's pretty easy to get a catapult to launch something consistently, right? If you've got a certain spot that it starts, you've got certain springs on it that are always the same tension, and you've got a hard stop that the catapult comes up and hits that never moves, it's going to do the same thing every time. So they're easy to get accurate as well. They're easy to build, they're easy to, or I should say they're easy to design, and they're easy to tune and get them to land the game piece where you want it. They're difficult to load, right? So you guys basically got to put a game piece in a cup, right? With a shooter, like a wheeled shooter, you kind of just need to roll a game piece in the end, and it comes out the other end a lot faster, which is pretty easy to do because typically you've got an intake mechanism. The intake mechanism is funneling the game piece up. You've got, you know, belts or rollers that are pulling the game piece up and in. It's typically easy to just kind of stick a shooter on the end of that, right, and just have it roll up and in your robot and then roll through and go into the shooter. Well, you've got a ball, and you kind of got to dump it in a cup, and then because you're driving around, you typically have to have some way to hold it still until you launch it. So loading a game piece into a catapult's kind of a pain. And typically you launch and then it draws back slowly because you've got it takes a lot of force to store that energy. And then you got to wait to load another game piece in. So typically catapults are used in situations where you can only hold one game piece. Right, like 2017, literally nobody ever at all used a catapult, right? Because you had to launch hundreds of balls very rapidly. You just can't do it with a catapult. Okay, so kind of another version of the catapult is a plunger, which is pretty simple, right? You've got a platen basically and a rod, and there's some sort of a spring, or it could be a pneumatic cylinder. Once again, sketchy on whether you can get that to work for a particular application, but in some cases it will work. You bring it back, it's got a lot of tension on it, put your game piece in front of it, and it punches it. Okay. Much more complicated than a catapult, okay, just because it's linear motion. Basically anything that's rotary is going to be simpler than something that's linear. Linear motion, for some reason, is just inherently a much more physically unstable process than rotary motion. I don't really have a good physics explanation for why that is, but just in engineering, you're always going to have a whole lot harder time getting things to move in a straight line than you are going to have getting things to move in an arc or a circle. That's just the fact of the matter. So if you can get something that rotates to work better than something that, or if you can make that work for you rather than having something move in a straight line, go for the rotary thing. You're going to have less problems with it. It's going to be easier to design. However, obviously a catapult has a big long arm and it swings, right? So you've got to have, the mechanism itself is fairly large, and then as it moves, it traverses a lot of space. And our robot has to fit inside of a certain volume, and so you've got to keep that whole volume that arm swings through. You've got to keep that all clear of other mechanisms. So not only is it a big mechanism, it also takes up a lot of space outside of where the mechanism is at any one point in time. Plunger takes up a much smaller space, and it moves in a straight line, so you kind of just got to keep a straight line path clear. You don't have to worry about it swinging. So it takes up less space, the package is nicer. However, it tends to be, once again, because linear stuff tends to be a lot less stable, it's less accurate than a catapult in a lot of cases. I mean, like I said before though, before I got into this, all of these can be made to work. It's just a matter of certain ones are just going to be, you're going to put a whole lot of effort into making something that's not really a good idea to begin with for that application work. Or you could just pick one that's a better choice for the application and put less work into it. All right, so let's go back. Let's rehash some pros and cons here. I've talked about a few of them, but I want to go over these in quite a bit of detail. Okay, so spoilers. The first one we talked about is the best shooter.
Whoa, really?
It is. It just is. Right? Like, basically. All right. Well, okay. Let's actually back up a little bit before that. If you can make it work, a wheeled shooter is going to be better than a spring shooter in nearly every case. Now, I don't really have a very good satisfactory answer for why that is, but it is undeniable given empirical evidence. So a good example, and probably the best example of this, 2014, that was when we took our first robot, which most of you weren't around here for, Coulter was. We had that big exercise ball. Have you guys seen that big exercise ball upstairs, one with like canvas covering on it? Basically, that was the game piece. You could only hold one game piece, right? You could only hold that ball. There was only one on the field per alliance. And so the game involved passing them back and forth. So you didn't spend a lot of time launching. You were launching a large object. Okay, you could only hold one at a time. And it was fairly heavy, had a lot of air resistance, and it was almost the same size as your robot. Okay, so it was difficult to physically fit a wheeled launcher on your robot. And that's the issue with the radial shooter, right? The biggest drawback of this design is it takes a ton of space and it's an obnoxious shape, right? It's kind of tricky to make this work in a design, especially 2013 with the Frisbees, because, you know, in a lot of cases, this is upright like this, right? And you kind of just bring a game piece in from the bottom and you chuck it out the top, and you kind of just rotate this depending on what angle of shot you need, depending on the game, right? If you need to be a more horizontal shot, you do more like that. If you want something more vertical, you do something more like that, so your release point's more vertical. In 2013, though, you laid those down, and you typically wanted to shoot up at an angle, but you were bringing something around at an arc, so it's kind of a tricky thing to do, and it took a lot of width. A lot of people tried to do a full 180 on it as well. And, you know, the Frisbee is 11 inches, you got like a 6-inch wheel and another 11 inches over here, and this mechanism just ended up being huge and didn't pack as well. So that's the biggest drawback of this. But going back to what I was talking about before, 2014, because of that fact, right, I've got to have a wheel that's spinning that has enough kinetic energy to launch this huge, fairly heavy game piece pretty far. And then I've got to have a wall over here for it to roll against. Like the whole the mechanism was literally front to back the size of your robot and the width of your robot too. So it was hard to package. Most people didn't even try. They were just like Catapult, right? That was a perfect application for a Catapult. Pretty much everybody used Catapults or punchers. We used a puncher. The Mavericks used a puncher. I'll talk about the puncher a little bit. The robot that's on the bottom of your page, this is the game that they were playing. If you want to look at good Catapult designs and puncher designs, they all came out in 2014 because everybody was doing it. However, when it all came down to it, at the end of the day at championships, this was back when there was only one championships. Basically, the game worked in such a way that you got points for passing the ball from robot to robot. So there's three robots on an alliance, and basically you would throw, a human player would throw the ball in the field, the robots would pass it to each other and then score it in a goal at the end of the field by shooting it into the goal. And the field was flat and wide open, so there was defense being played. And so basically what you would do, typically by the end of the season, you would have a robot that was a designated inbounding robot. So you have kind of your simplest, least competitive robot on your alliance, and they would take the ball from the human player, right? That was a fairly easy task, at least at championships it was. Then you would kind of have a good middle robot who would take the ball, and there was actually something that you launched it over in the middle of the field, but I'm not going to get into that. Basically, that robot would then pass it to the next robot, and then the last robot, which was typically your best robot, was what they usually called your finishing robot, and that would be the robot that would actually score the ball in the goal. Okay, that was the most difficult task in most cases. The finishing robot on the winning alliance at championships and the finishing robot on the finalist alliance, the runner-up alliance on Einstein at championships. So basically, the two best robots in the world were both wheeled launchers. And they were like the only ones, right? There were only a few teams that even did wheeled launchers that year, much less did it successfully. But the two robots that were finishing cycles at the end of the season were the two best wheel launchers, and Catapult launchers couldn't keep up with them. I, once again, don't have a good satisfactory answer for why that is. I think it has something to do with wear and tear on the mechanism. I think it might have something to do as well with controllability. You can change your shot by adjusting wheel speed, and that's easy to do with programming, whereas with the Catapult, once you build it, it's harder to adjust. Shot release point definitely played a factor. The design of the wheeled shooter allowed the shot to be released from higher up on the robot than a Catapult would. That might be counterintuitive, but that's just how it worked out with their particular designs. I think in that year, a lot of teams retracted their Catapults too slowly, and so they have to wait for it to retract to bring a ball in, whereas a wheeled launcher, you can spin the wheels up while you're getting a game piece ready. So I think there were a lot of factors that play in, but it's a fairly common thing that wheeled launchers at the end of the season outperform Catapults. There's going to be good Catapults. Like I said, you can make it work. Right? I mean, all the other robots on those two winning alliances were Catapult robots or Puncher robots. Puncher robots kind of lost out fairly early because, like I said, rotary motion tends to win out. The Puncher robots lost. They were good. There were good Puncher robots, but the Catapult robots ended up being more effective in the end. But wheeled launchers are pretty consistently good. So, a couple minutes here before I want to get to CAD. So I mentioned packaging was an issue for the radial shooter. Okay, the linear shooter solves that at the expense of complexity. Right, you've got more wheels. The disadvantage of the linear wheeled shooter is also that the game piece kind of like does that as it goes through the shooter because it kind of bumps over the wheels, and that is definitely a concern. It's something that happens. Typically, one mistake that people make when they're designing a shooter is they don't put enough compression. Typically, you need to squeeze the game piece way more than you think you need to. Right? You squeeze the game piece and you're like, oh, that's way too much. No, that's probably how much you need to squeeze it. Because it's typically, if you got a ball that's this big, you need to squeeze it like 2-3 inches. I remember in, I don't remember the exact numbers, but in 2012, the Get basketball year, it was an 8-inch ball, and it was fairly soft foam. It was a Nerf basketball, is what it was. And the good shooting robots at the end of the season were squeezing the ball down to like half its size or something crazy like that. I don't remember exactly what it was, but they were squeezing it a lot. Anyways, so when you're squeezing something that much, it'll still make contact when it's in between wheels, right? Because it'll just expand, and then it'll get compressed as it goes around each wheel. But that, that's harder to get working. It's not as efficient, right? Because you've got to spin all these up faster because you've got less contact time with the game piece as it goes through, where you've got perfect contact as the game piece rolls through here. So you can make this work at the expense of complexity, and it's going to take more tweaking and tuning, but if you can't fit this in your design, this will work. If you're launching a ball, you shouldn't do opposing wheels. You just don't do it. If you think you want to do it, don't do it. It's just, the spin is too important, is really what it comes down to. A lot of teams try it. I've never seen it work well. This year was really the first time I've seen it be an actual good solution because it was a cube and you didn't have wheels on both sides. But once again, you were launching it on top of this huge platform, so you didn't need to aim that well, and you were launching it from the floor up to about here, so it was like just a little lob. So I hesitate to even call it launching because of what it was. Okay, so we ended up talking a little bit more about catapults. The big issue with catapults is reset time, right? How long it takes to draw the catapult back, how the catapult is loaded. Catapults are becoming easier and easier to do. Catapults are becoming more effective in years where game pieces can, we can only hold one game piece. I've only seen one example of a catapult in a year where we could hold more than one game piece, and that was also the basketball year. That robot ended up winning championships, but they won championships because they were a defense bot. not because they could shoot, because they couldn't shoot, because they had catapults. They basically, I mean, they would, I think it was a pneumatic launcher too, because the pneumatics rules were a little bit looser then. I think it was pneumatic. And basically they would launch the basketball, they would bring it back real quick, they would plop another ball on it, and they would sit there, but they were slow because they had to cycle the balls, whereas robots that had these launchers, which were the vast majority of them, could just poop, 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 and go and, you know, pick up more balls and go shoot, because you could hold three. You could hold three at a time. The robot that I've got pictured here under Catapult, it's 148's robot from 2016, so 3 years ago. That 148's a really good team, one of the best teams in the world, and they built a Catapult. 118, a lot of you know who 118 is, they built a Catapult that same year too. Obviously, you can do it, good teams do it. However, at the end of the day, the wheeled shooters won. 254 did a wheeled shooter and they could shoot circles around everybody else. There's a pretty nuts video of 254 on the practice field that year. It's just crazy how much better they were at shooting than everybody else. Just sickening, but I watched it over and over anyways, it's cool. Any questions on launchers?
How did the Mavericks do that year with the
We did okay. So I was a senior that year, and I was pretty much the only CAD student. And we got snowed out for 4 days at the beginning of the season. So I did about 95% of the CAD on that robot as a student my senior year. And we did most of it at my house, like while we were snowed out at the beginning of the season. And I made some mistakes. So overall, the robot was good. It was basically an arm that had rollers on it, and the arm would raise. It would go down. The rollers would pick up a ball. They would just pull it into the gripper of the arm, and then it would go up. The top gripper would open, and the puncher would fire it out. It was a fairly common design. It was based off of a robot of 1114s from 2008. So overall, the concept was sound. It was the best Maverick robot to that point. Not competitively, but in terms of design and actual function. I'm pretty sure they've since outperformed it, but we were finalists. We were captain of the finalist alliance at Buckeye. We didn't win anything, we didn't go to championships, but I mean, it performed well. There were a few weak spots, stuff that I just missed, because, you know, I was the only one working on it, and I missed stuff and I made mistakes. That kind of ended up taking it down at the end, but I mean, it was good, it worked.
Yeah.
That puncher was scary though. It had like 160 pounds of spring force on it or something. I mean, you put your face in front of it, you were gonna die. Like, we were pretty skittish around it all season long, but it's pretty impressive to take the demos because it would be a big boom as it would hit the ball and the ball would go flying, you know. It was pretty good. There's videos of it up on YouTube. We did a release video that year, so there's also a release video of it. All right, that's it on launchers. Launchers are a thing, so we'll talk more about it when we get into the season. FTC, you guys don't use launchers nearly as much. FTC has trouble with wheeled launchers just because of the power of your guys' motors. So wheeled launchers are not nearly as common or effective in FTC as they are in FRC. However, they're becoming more prevalent because the hardware is there that you guys can make high-speed launchers. I think it was, what year was it that you guys did the like the fork thing on the tree stand? What was that? It was Velocity Vortex. Yeah, there were some wheel launchers that year, and that was kind of the first time that they really got used in FTC. But
The fork thing.
I don't.
Yeah,
the
fork thing.
Also, FTC students, I'm actually going to be mentoring FTC this year for the first part of the season, so for CAD, and then once FTC or FRC gets going, I'll cut out to do FTC. Okay, Inventor. So we're using Inventor 2019 because that's what's installed in these computers. Like I mentioned earlier, if you save a file in Inventor 2019, you cannot open it in Inventor 2018. It's not backwards compatible. So if you guys have 2018 at home, you're not going to be able to edit these files that we make today. I would advise just uninstalling Inventor 2018, going through the same process that you did to install Inventor 2018 and just downloading Inventor 2019 and installing it. We're going to be using, both FTC and FRC are going to be using Inventor 2019 this year. There's not really any changes. There's one change that we'll talk about, but that affects us. Most of the other changes don't affect us, but yeah. And because we're in this classroom, we've got to go through and change our settings again. If you don't remember how to do that, yes.
I didn't even know if I download it.
Actually, what we're gonna do, you don't need any of the past files for. We did that gearbox thing. I'm gonna put up a video again of me going through that.
Oh, I already got it.
Oh, you got that done? Okay.
I was, if we're looking at
We're gonna continue our project. I think you should be good then. If you have the gearbox, we really didn't get much else done last week. And like I said, I'm gonna have the video out again, so if there's anything that you missed, it'll show you how to do it. Yeah. Okay, so I'm gonna change the settings. Make sure you activate your project file. Why is my screen resolution so low? Please.
So there's no way you can update from 2018 right then?
No, I don't believe so.
Okay.
I've never tried. I mean, it's actually a different piece of software.
Oh.
It's not like, you know, updating Windows or something. I think the only way to do it is just to download it again and install it. You can have multiple copies of Inventor installed on your computer. So if you don't want to uninstall 2018, you can leave it on there. But I mean, we're going to be pretty much using 2019 for everything from here on out. So I would just leave it up. I installed 2018 on the new FRC CAD laptops and regretted it instantly because I'm like, why did I do that? I'm gonna have to install 2019 like in a month. So now I gotta go home and I gotta install 2019 on my home computer, the 2 FRC computers, the 2 FTC computers. Like,
So can you still open files from like saved things?
right, you can open past files.
Okay.
So 2019 can open 2018, 2017, 2016
Yeah.
files. It's just once you save it, it becomes a 2019 file.
Okay.
Okay, that's it. All right, so what we're gonna do here is, did we do a layout sketch? We didn't do a layout sketch last week, did we? Okay, so, projects, compare, browse, thumb drive, Stellar CAD class 2018, Stellar CAD class 2018 project file, open, done. Okay, so I'm gonna open our gearbox. You guys don't need to do this really. Well, you can. It doesn't matter to me.
Dude, why would you do that?
You guys remember this? Okay.
Yep.
All right, I talked about this 2 weeks ago, a week ago, whatever. I'm gonna go over it again just for those of you who weren't here and just as a refresher. So what we're gonna do, we're designing a pickup mechanism, right? Normally this would be a large mechanism that would fold out of the robot. We're gonna kind of design just the tip of it, that's one roller and a gearbox to drive that roller. So we're gonna have 2, looking from the top, we're gonna have 2 frame rails. We'll talk about those in a bit. They're gonna be kind of special. They're gonna be made out of sheet metal. This is what we're gonna try to get done today. There's gonna be bearings here and here on both sides. There's gonna be a hex shaft that goes all the way across. And there's gonna be a drum roller on here, on the hex shaft. There's gonna be a GT2 timing belt pulley here. There's gonna be a GT2 timing belt pulley here and a belt connecting them. The gearbox that we've got right there, here's the gearbox. Here's the motor shaft. Will be there. And there's gonna be some special mounting structure that we use to mount the gearbox in that position. Everybody clear on exactly what that's going to look like?
Yep.
Alright, so what we're going to do is we're going to make a layout sketch of this region here looking from this side. Alright, that's all we got to care about. All this other stuff we don't need a layout sketch for, we'll just figure it out as we go. But we need a layout sketch basically to figure out how far apart these two need to be. Okay, now did we pick a belt last time? I don't think we did pick a belt. I showed you guys the calculator. Did I show you guys the belt center
Yes.
distance calculator? Okay. We kind of got like halfway in between. So let's start a new part.
I hate you so much.
Just a new standard.ipt part. Basically, we need to draw just a few simple shapes. This is going to be pretty easy, so we're going to blow through it as quickly as we can so we can get on to some other stuff. I hope to get this done last week, and we just didn't. So I'm just going to check to make sure we didn't. Okay, we're going to start with a circle on the origin point, 1.25 inches in diameter. And Coulter, you're our last man standing. You have to help people if we lose Coulter to college next week.
Oh.
So,
Alright, Coulter.
it's just going to be me in here teaching. So.
Oh.
Alright, so that's going to be the metal portion of the roller. It's going to be a tube that's 1.25 inches in diameter. We're going to add some grippy rubber on the outside of that to be grippy. So we're just going to offset a circle. We click the offset tool. We're going to offset by 1/4 inch because the rubber is going to be, guess what, 1/4 inch thick. Now I want to draw a circle on the outside of that that's another 1/8 inch past that because I want to just represent a region of no intrusion, right? I don't want, yes?
This is just standard, right? You want to do a sheet now?
Right.
Okay.
It actually wouldn't matter because we're just doing a sketch. We're not going to do an extrusion, but yeah. All right, so I'm going to click offset again. Click the outside circle I just created. Actually, I'm going to turn on construction geometry. Click the outside circle I just created and do 0.125 or 1/8 of an inch. Now, this basically just represents a buffer region. I don't want anything to get inside of this. I don't want anything to interfere here, right? Because I don't want anything to get too close to the rubber. You know, we want a little gap, basically. So this is just a visual reminder to tell me how much space I have, okay? But this is the actual mechanical outside of the roller. This would be rubber or something. All right, next we're going to use a center point rectangle. Actually, no, we're not. We're going to go over here. We're going to represent this gearbox in our layout sketch as a square. In reality, there are these little like bumps here that stick up, and it makes it not really a square, but the flat parts are square. And if we go to the measure tool, get millimeters here, it is 42 millimeters in that direction and 42 millimeters in this direction. So, with that in mind, we're going to draw a 42 millimeter by 42 millimeter square in our layout sketch. So, click 2-point center rectangle. Place a point down here, somewhere in the middle. Place the center point. Move your mouse out from there. Type in 42 mm for millimeters. Press the tab key. Type 42 mm. And press enter. Alright, so now we've got this square that can kind of just free float around. We want to line it up horizontally to the center point of the roller because we're going to keep everything in a flat plane. So gearbox, roller, belt, it's all going to be flat, right? It's not going to be up top. So click the horizontal constraint button. Line these up horizontally. Okay, so now the only thing that we have to do, so if I put this here, what would happen? If I put, this is the gearbox, remember, if I put the gearbox here, what would happen?
Lots of things.
could interfere with the rubber.
Right, it would be hitting the rubber basically. So we need to have this, if it was here, would it be interfering with the rubber?
Yes.
No.
What?
This dotted line is just a marker. This is actually where the rubber ends.
Oh.
However, the reason that I have that dotted line there is because I don't want us to get too close to the rubber. Right? So basically I want us to be on the outside of this dotted line, because if we were inside that dotted line, we'd be interfering with my safety zone that I had defined. I just put that dotted line there as a visual reminder. You wouldn't actually have to do that, it's just something that I do. Alright, so now we need to pick a set of sprockets or a set of pulleys and a belt to join these two together. So let's go to Vex's website here. I'm gonna go up to Motion, belts and pulleys. Everybody getting there? Colt, you wanna have a look around, make sure everybody's getting to the
In the motion network?
Motion, belt and pulleys. You're gonna go to GT2 timing pulleys, which is right here. Scroll down a little bit. Alright, so we scroll most of the way to the bottom. Basically, I didn't talk about pulley diameter last time, did I? See, the problem is I recorded the video for this like 2 days ago or something, and I'm mixing up what I talked about last week versus what I talked about in the video. I'm trying to make sure I cover the same thing in both places. Okay, so let's see if I can explain this a little bit. All right, if I have a belt running around the pulley and I put a certain amount of tension on it, what's going to happen to the belt? Like a large amount of tension, what's going to happen to the belt? It's going to snap, right? The belt's going to break, okay? Or typically the failure mode for a belt is it's breaking. It might be teeth stripping. That could happen too. But basically, there's only so much tension that I can put on the belt before it fails, right? So that's the constraint, right? I'm constrained to a fixed amount of tension on the belt. That's how much the belt can take, okay? But what I care more about in my application is probably torque, right? I really don't care how much tension is on the belt. I just want the belt to transmit torque. That's what we care about, right? So if I have a little tiny pulley and I'm putting, 1,000 inch-pounds on it or something, right? And I've got a belt that goes around it and drives something else or is driven from something else. Okay? There's a lot of torque, or there's a lot of tension, there's a lot of torque and a lot of tension on that belt, right? So 1,000 inch-pounds on this pulley here. Okay? There's a lot of tension on that belt because my pulley is very small, right? There's not very much leverage there, right? The belt doesn't have very much leverage on the pulley. So if I make this pulley bigger, and there's still 1,000 inch-pounds on it, which really isn't actually that much. 1,000 inch-pounds really isn't that much, but I mean it's a lot, but not that much. Both sides of our drivetrain together might generate 1,000 inch-pounds at stall. I'm not sure, but is there more or less tension on the belt if we make that pulley bigger?
Less, because the actual pulley is taking more stress.
It's a little more subtle than that. There is less. It's really just because the pulley is farther away from the pivot point. Okay, this is a little tricky. Remember when we talked about torques and moment arms? And we were using a force and the length of the moment arm to figure out a torque. This is the opposite of that, right? We know the moment arm, which is basically just the radius of the pulley, and we know what the torque is, and we want to figure out how much tension is on there. So it's basically backwards, but basically, as I make the moment arm longer, but the torque is the same, my force at the end must be getting less, right? And if you think about that, it makes sense. I mean, if you've got a bolt, right, that's being a pain in the butt and you can't get it off, what do? Well, get an oxyacetylene torch, get that bad boy off there. No, typically you get like a bar or something or a tube and slide it over your wrench. You know, they call it a cheater bar, right? You basically make your wrench longer, right? You give yourself more leverage. I mean, that's fairly intuitive. So it's kind of the same thing here. I use a bigger pulley. The belt is farther away from the pivot point. So for a given amount of torque, there'll be less tension on the belt. Okay, so if all else being equal, do we want a bigger pulley or a smaller pulley? All else being equal, we don't care about anything else except what we're talking about here.
Bigger pulley.
Bigger pulley, because it puts less tension on the belt, right? The less tension on the belt.
Belts.
What?
In which case, a very small pulley.
What's that?
Unless you hate belts.
Right.
wanna
Yeah,
find
if you have something
something
against the
like
belt,
that.
you want to put it on small pulleys, because then it'll break and it'll die. But we love belts. If it was a chain, we'd be picking a real small sprocket.
Cause you need cold chain.
We're gonna call you back from college. You get to change the chains. Okay. Culture's like that. Okay, so we want to pick a large pulley if we can. Now, in our design, we have a roller, right? Okay, this roller is rolling in game piece. What happens if we have a pulley that's bigger than that roller? Well, probably the game piece could hit the pulley instead of the roller, which might be a bad thing. Okay, so ideally, in an intake like this, you don't want the pulley to be bigger than your roller. If you don't have a choice, you can fudge it a little bit. It can be slightly bigger, but ideally it's smaller. So we want to pick a large, actually let me back up. We're going to do a 1-to-1 ratio. So we've got our gearbox, we've got a pulley on the gearbox, a pulley on the roller. Those are going to be the same pulley. We're not going to do any like small pulley, big pulley stuff between this. We're doing all of our speed reduction in our gearbox, and then we're just using the belt to move the power, right? To move the rotational motion. So basically, we need the large. So basically, if we use a large pulley, it doesn't change our gear ratio, right? The big issue is, you know, sometimes you need a real small pulley and a real big pulley, and so you don't really have a choice. But in our case, we can make both pulleys bigger or smaller in diameter at will, because it's not going to change our gear ratio or our belt ratio. Not actually a thing. Basically, we want the biggest pulley we can get that's still smaller than our roller, essentially. And then obviously, if you start getting pulleys that are too big, they start adding weight, and at some point, you know, you're so far within the belt's tolerance that we don't care. But in this case, you know, the pulleys aren't going to be very big, so they're not going to add going to bigger ones not going to add much weight, so we don't care that much. So I'm going to VexPro's website. Now I just want to know, all I care about is the outside diameter of the pulley right now. Right? I don't really care about tooth count. Yes?
Real quickly, is it the GT or HTD?
GT. Okay, so I'm going to drawing, mostly down at the bottom of the page. Click on drawing, and I'm clicking where it says 1/2-inch hex bore timing pulleys. Click on that. It should open a PDF right here. So basically, it's got a drawing that shows some generic dimensions, and then it's got a table that says which pulley corresponds to which dimensions for those. So we're worried about outer diameter. All right, so we want to go and we want to look at all the outer diameters. We want to look at which outer diameter we want to use, and then look at which pulley that is, how many teeth and which pulley it is. So 1 inch. Okay, let's go back to our. This is what we're worried about. This is the roller. I'm going to use the measure tool to measure that. It is 1.75 inches in diameter. Okay. 1.75. We can't go larger than that. So outer diameter of 1 inch. Okay, great, that's less than 1.75. We want to go with the biggest pulley we can fit that's less or equal to 1.75. So the next one, 1.535, right? That's bigger than 1 inch. That's great. That reduces tension on the belt, makes it less likely to skip. So well, let's keep going larger. Next one is 2.008 inches outside diameter. That's bigger than 1 3/4. It's bigger than 1.75, so we can't use that, so we gotta go back to this one. So this is gonna be our guy. This is gonna be our pulley right here. So it's a 36 tooth pulley. So we're gonna use the 36 tooth pulley. So now that we know which pulley we're gonna use, jump over to CAD Files tab. We're gonna grab the CAD file for it. This guy right here, 36T by 9mm wide, double flange aluminum pulley. So click download. Should be third from the bottom. 36T. Download. Show in folder. Go ahead and cut that out and paste it into your CAD class folder for this project, your drum roller project. Okay. Well, we're going to use that. We're going to use that CAD model later, and we probably aren't going to use it in here. All right, so let's. Well, we know the outside diameter, so let's.
What constraint did you put on that square to get it down on the?
So it's horizontal like this, so it's sliding back and forth. So yeah, horizontal constraint, and then just put the center one of the circle in the center. Okay, so let's draw our pulleys in our layout sketch here. So there's going to be circles. We know that the outside diameter was 1.535. So we're going to draw one on the gearbox and one on the roller.
What was the dimensions for that?
1.535. I don't know if that showed up on that screen very well. Okay, you guys got those circles in your sketch?
Yep.
Alright, so basically what we want to do is we want to pick a belt. In the video I drew some lines. You can do that if you want. You can draw a line. You don't really need to do this, it doesn't really matter, but I did it in the video. We're not going to do it here today. Okay. So basically we need to pick a center distance, right? We need to pick a belt and figure out what this center distance is, how far apart these are. So let's go back to Chrome. Let's go to Motion, Belts and Pulleys. It's going to be GT2 timing belts, 9mm width. All right, so these are our choices right here. We got 45 teeth all the way through whatever it is, 180. So, what is the disadvantage to having a really long belt and having the gearbox way over here? Space, right? There's no reason to put it way far away from what we're driving. We don't have to. Now, in some cases, maybe we do, right? Maybe there's some good reason to do that, but in most cases, no. We want to put it close. So, we want to pick basically the smallest belt that we can that still makes the gearbox not interfere with this dotted line right here. Okay. So let's go back to Chrome. Let's go to sdp-si.com. So we know we're using 36 tooth pulleys, right? Okay, so we made a decision on that. Now all we need to decide is how many teeth our belt has to have. So go to Design Tools, which is this button up at the top. Hover over that, and then go down to where it says Center Distance Designer. Click on that. Alright, so under Units, we're going to pick a bunch of options here. Units or metric. Our pitch is going to be 3 millimeter GT2. Somewhere in the middle of that drop down list. And then pick where pulley A and pulley B are. Pick the number of teeth for each pulley, which is 36. You have to scroll down to get to 36 teeth. Okay, so it's going to be 36 in both of these places, here and here. Alright, so you can do this one of two ways, and I believe I talked about this a little bit last week, but I'm going to go over it again because I don't know what was in the video and what we talked about in person, because I'll remind you that. You can either type in a center to center distance that you want in millimeters, and it'll give you the closest belt that you can get to that, or you can select the number of teeth of a belt from this list, and it'll tell you what the center to center distance is for that belt and the pulleys that you've selected. Okay, that's what we're going to do because we have a list of belts that we can use, and we don't really care much what the center to center distance actually is. We just want something that is close to this, so that those two shafts are close together, so they're not wasting space. All right, so let's just start at the top of the list. 45 teeth here. Actually, no, we're not going to start with 45 teeth. I know that one doesn't work. We're going to start down here at 60 teeth. 45 teeth is tiny. That's a tiny belt. So we're going to start here at 60 teeth. So if we go to the SDP thing, and we go to this drop-down list here at the bottom, we click on the drop-down list, and we go up to 60. Click on 60. Now, it automatically switches to 62, which tells us something not so great. Basically, we can't use a 62 tooth belt with these two pulleys, because basically what would happen is you've got the two pulleys, which are round, right? And basically, you get them close enough together, the two pulleys hit each other. Right? So a 62 belt is so short, the two pulleys are running into each other. So the shortest belt that we can use is 62 teeth. Right? And Vex doesn't sell a 62 tooth belt. They sell a 60 tooth belt and a 70 tooth belt. So the next size we can use is a 70 tooth belt. So let's go back to the SDPSI thing, click the drop down list again and go down to 70 and click on that. Alright, it's happy with that, leaves it at 70. We can see up here under center distance where it says actual, it tells us 51 millimeters or 2.0079 inches. We're going to use millimeters because it's a nice even number because we're using metric belts. So back to Inventor, grab a dimension, click the center point of your roller and the center point of the gearbox. So dimension between these 2 points here. Place the dimension down somewhere and type in 51 millimeters. Now remember, this is the smallest belt that we can use. We want these to be as close together without running into anything important. Okay? This is the smallest belt that Vex sells that we can use with our two pulleys. So, do we have any interferences in our design? Yeah or nay?
No.
No, we don't. So this is good. Nothing's running into each other. We got plenty of space. We got plenty of space between the gearbox and our zone here that we don't want to go inside of. Can we get these any closer together using belts from Vex? No, we can't because we're using the smallest one that they have that fits. So is that the belt we're going to use? Yes, it is. All right, so we're done here. This is all we needed. This is all we needed this layout sketch for. The only thing we needed this layout sketch for was to evaluate which belts and pulleys to use. So it served its purpose. It's done. Finish the sketch. I'm going to give it a save because we might want to come back to it later. I'm going to call it
So you finished the sketch.
Yeah, finish the sketch. Alright, so because I want to get to it, because it's kind of the meat and potatoes of the design, I don't think we're going to get through it in a half an hour, but we're going to try. I finish it in the videos, so I mean, I want you guys to finish this. We're not going into a project in the next 2 weeks. In the next 2 weeks, we're going to learn how to do drawings like that, like prints. So I'm going to teach you guys how to do that. We're going to try to go over some exploded views. So if you guys want to take an assembly and explode it out, we'll probably take our gearbox that we designed and we'll explode it. That's not, it's finicky, but it's a good thing to be able to do. So we'll probably just mess around with that. It should be pretty easy. And then the last 2 weeks of the class, the following those 2 weeks will be another project again. So you guys want to finish this on your own time. Also, because we're going to be using the gearbox, make sure you guys have that finished and on your thumb drive. All right, so
what is there to finish with this?
with this,
Yeah.
we're going to put the whole assembly together.
Oh, okay. Are you gonna like do a speed video on it?
Yeah, I've already got some of them done. I need to finish them. I'll probably go home and record a bunch tonight and then upload them. I've got 2 done so far. It's probably I think 2 or 3 videos. This is a more advanced project than the other 2 that we've worked on.
What did you name this layout and stuff?
I named it Stellar Robotics 2018, CCDR for CAD class drum roller, and then just layout 001.
Alright.
That's the naming convention that we use. I'm not going to bother teaching it to you guys in the class, but we use it on the robotics team and FTC students. I'll show you guys. We'll come up with something. We'll just do like, I don't know, HR for her kid or something, and then a year, and that's what we'll use. Okay, so let's talk about, I had a really hard time explaining this in the video because I didn't have a whiteboard or my hands so I can draw in the air and pretend like you guys understand, but you really don't because you don't know why I'm waving my hands around. Yep. I talk with my hands, but nobody knows what my hands mean, so really nobody understands what I'm talking about at any one point in time. So it's like, did you guys get all that?
Yeah, definitely.
The homeschool group I was in, we did sign language classes, and I was just really bad at it. Alright, so basically, we've got 2 side rails. I shouldn't have erased that. I've erased that. We've got 2 side rails, like structural components. Okay, now Stellar Robotics uses sheet metal. That's stopped in sign language. Okay.
He doesn't. He failed, Simon.
I failed hard, yeah. This is taco. This is taco. This is stop. That's what I remember. I remember the alphabet too, but what was I talking about? So, all right, so we've got basically 2 side rails that the gearbox is going to mount to. We've got to attach bearings to it. They're going to be kind of rectangular. A lot of teams would use a piece of aluminum tubing. Okay? Now, never mind, I'm not going to go into that. Okay, so we basically need to create some rectangular structures that are strong, right? Because an intake is typically the front of your robot. It's going to get run into. If you think your intake is going to get run into, it's going to get run into. That was the big mistake we made in 2016. We were kind of like, I probably won't get it run into. It got ran into. And every time it got run into, it broke. And then we couldn't pick up balls for the rest of the match, and we couldn't score points because we couldn't pick up balls. That's how life works.
Yeah.
Right.
Deja vu.
I don't want to talk about it. We don't make the same mistakes every year, I promise.
No, never, just 2-year gap. Just
We go on a rotation. All right, so we've got those 2 side pieces and the roller's kind of in between them, right? Because Stellar Robotics uses sheet metal, we're not going to make these out of tubing, which is what a lot of teams would do. We're going to make them out of sheet metal. So we gotta get a little creative with it. I just like this way of doing it. We haven't done it quite this way in the past. The way we did it on the 2016 intake was almost good, but it wasn't. So we're gonna do it a little bit differently than we did that. And we're also gonna be a little more generous on our space because we're not so tight in terms of space. So what we're gonna do is we're gonna kind of form a box out of sheet metal. Now, normally on a mechanism, these would extend back and there'd be other structure. So we're literally just kind of going with a knife, and we're cutting it off. And we're just gonna end the mechanism. We're not gonna worry about what goes on. We're just gonna make these kind of short and stubby, and we're not gonna care about them a whole lot because we're only really what we're worried about is the roller. So we're gonna take it easy on the structure a little bit, but we're gonna model it the way it would look if we cut it off. So basically what we're gonna do is we're gonna take two channels of sheet metal, right? So flat face of sheet metal with a flange on the top and a flange on the bottom, right? That are gonna be like this, okay? If I draw a front view of this channel, then we're gonna take another channel and we're gonna go outside of that. Okay? And these flanges will overlap and there'll be holes in the top and the bottom, and then we'll rivet them together. So essentially what we've done with sheet metal, we formed a piece of box tubing. Now, we're gonna do one other thing. We're gonna add flanges on the ends as well that will overlap so that we can have rivets down the front. So we'll have, you know, a flange on this, and then over top of that there'll be a flange coming from here, and they'll have holes. Right, and that'll add strength in another axis, because basically if you just have a tube, you can rack the tube, right? You can do this with it, or you can just squash it, right? But if you kind of box off the end, it adds a ton of strength. Okay, so that's why we're adding flanges on the end too. So essentially what we're going to do is we're going to have two. We're not going to do that on the back end though, so this end isn't going to have a flange on the end. Because, like I said, we're cutting it off and we're not worrying about that end, so we're just going to kind of end it, right? So essentially we're going to have a box, I'm trying to do this, that's like a flange and a flange and a flange, and then we're going to have another box that kind of goes over top of it like that, right? Except it's going to be a rectangle, not hand-shaped. So, let's decide how big. They're going to be rectangular, just to make it easy. There'd be some cases where you wouldn't make it a rectangle, you might make some other shape, but we're gonna do this one. Okay, so new sheet metal part. Bless you. Click create. All right, so we're gonna design this around. Now I mentioned there's gonna be bearings on either side of this. So these pieces of sheet metal parts are gonna have holes for bearings in them. We're not going to get to bearing blocks today. I talked about it in the video. Watch the video. All of them. All like 5 hours. It's going to be a long.
They're usually about 4.
About 3.
About 3.
Well, I think the gearbox was 2 hours and 40 minutes, and I think the pneumatic joint was like 3 minutes. Okay, so we're going to start with the circle. That is 1.125 or 1 1/8. I think you can also do that. Yep.
Yeah.
All right, 1.125. Also, I think that's a new another inventor 2008 or 2019 thing is that actually shows up as a fraction if you type it in as a fraction. Inventor 2018 didn't do that, so that must be new as well. Okay, so 1.125, that's 1 1/8 of an inch. This is going to be a hole. This is going to be the hole that our bearings go into in one of these boxes, okay, or in one of these pieces of sheet metal. So this is going to be if we go back to our layout, this is going to be the center of the roller, basically. So we want to give ourselves kind of a box around everything that's going on here. Okay, we're going to do, this is like 1 3/4-ish, 42 millimeters. This is 1 3/4 exactly, the actual roller. we're gonna give ourselves some generous space on either side of that, so we're gonna go 2.5 inches tall. That's just the number that I picked. Talk about a little bit more detail in the video, but for time's sake, we're not gonna go into it here. Now, that means we're gonna have 1.25 inches above the center of the roller, 1.25 inches below the center of the roller, okay? And anyways, so we're gonna have 1.25 inches above and 1.25 inches below. I want 1.25 inches in front as well. And then we just want it to be back here somewhere. Okay. So, just like I said, we're cutting it off, so we don't care much about that end. So what we're gonna do is we're gonna go pick a normal rectangle, a 2-point rectangle. We're just gonna box around this like that. Press escape to get out of that. Then what we're gonna do is we're gonna use a horizontal constraint. Okay there, Jim?
Yes,
Alright.
mental fit.
Okay, so horizontal constraint, Colt, you might need help. Pick the center, basically what we want to do is we're going to center this rectangle vertically on our hole here. So pick the center point of one of these end lines, find the green dot and click, and then click on the center of the circle. Find the center point of one of the lines. It could be this line as well, it doesn't have to be the front one, but the front one makes more sense to me, so that's what I did. So now our rectangle is constrained symmetrically, top and bottom. So now we're just going to dimension the height of this to be 2.5. I'm listening to when I hear keyboard typing, I know that's a good sign. Okay, so we're also going to dimension from the end of this rectangle to the center of the hole, and that's going to be 1.25.
That's a lot of keyboard typing.
We're also going to make it 5 inches overall length. It gives us enough space.
Oh wait, sorry.
Alright, now I lied a little bit on these dimensions. So this is what, when we make this box, right, that fits together, we want the outside dimensions of it to be this. But we're modeling the inside part right now. Okay, so it needs to be smaller than the overall size, right? Does that make sense? Okay, so the material thickness we're going to be using here is a 1/16 of an inch. Okay, so we need to take this dimension, actually delete this 5-inch dimension, and dimension from the center point to the back. I think I made that mistake in the video. But anyways, you want the dimension from the center point to the back to be 3.75. It gives you the same overall result, but because of what we're about to change. Okay. So the 1.25 inch dimension, you need to subtract 0.0625 or 1/16, which is the material thickness that we're going to be using. 0.0625, just subtract it and click OK. And then in the 2.5 inch dimension, you need to do that twice because you've got the top and the bottom that you need to worry about. So just type in minus 0.0625 minus 0.0625. Or minus 1/16 works as well.
Twice inside the dimension?
Do it twice, yeah. Just minus 0.065 and then minus 0.065 again. Right, but then you've got to use parentheses.
Wait, do I do it in times square?
Not this one. You actually, yeah, you don't.
What was the one we did before that?
What's that?
What was the one we did before that? That we just.
This one?
No, that one.
Yeah, just once, just one, just minus 1/16. So what is 2/16 in decimal?
Oh, because, oh, no, it's 1, 0, 0. There you go.
Okay, finish the sketch. We're done here.
Finally.
Wait, so you don't need to subtract, we don't need to subtract the 16th from that second dimension on the top, the 3.75.
Yeah, because there's not gonna be a plan to get that. That's why I had to change from the 5-inch dimension to that dimension, because we didn't. All right, now we gotta set our sheet metal defaults. So I set our material thickness to be what it is supposed to be. So click on sheet metal defaults on the sheet metal tab, check, uncheck, use thickness from rule. The thickness is gonna be 16. Sheet metal defaults, and then uncheck, use thickness from rule, and the thickness is gonna be 0.065.
Oh, just origin.
Wait, how big do I want it? Stop.
What?
0.625.
Get it?
Yeah.
Okay.
Alright, so click OK in the dialog once you've done that. Now, we need to create a face feature to turn this into actual sheet metal. You good, Coulter?
Yes.
So click face, click the region that you want to become a face, which is this region. I'm going to flip the direction to the other way because it just makes more sense to me to do it that way. So it's this button here. It won't make a difference though, so don't worry about it. I mean, do it, but don't. If it's confusing, don't worry about it.
It's not giving you an option.
Right, you don't. Micah, these buttons here.
Yeah.
You don't have those?
No, I don't.
Have you selected your region?
Yeah.
Yeah, he doesn't have them.
So I applied using Better 2020.
Oh, you're using your computer. Okay. Yeah, it's gonna be. So okay, so that just toggles it. So this must be a difference between Inventor 2018 and 2019. So when you click that button, Micah, it just flips the direction, and you click it again, it flips it back, which is. I'm not surprised that they switched it to this, because this is how it is in pretty much every other. Yeah. I didn't even notice that this dialogue was different, but it is different. Yes.
Why won't let me like edit any dimensions? Over constrain it as such.
Yeah.
Can you help me?
He's too busy. He doesn't.
Coulter's is like, yeah, you know what this is. I'm not listening. He needs help. I'm busy. Well, it still has a gap. Alright, click OK once you've done that, guys.
Okay.
Alright, so now we gotta add some flanges.
Hands.
Click the flange tool.
Well, has to be.
The material thickness,
Yeah.
0.065.
You're good at all. We're doing this
Did you
twice.
uncheck the thickness for roll?
0.625.
Anybody know what 0.325 is in a fraction?
Order of magnitude.
Just put on exit 200.
Robotics.
When I started my internship at
Flat charts, one yeah, huh? Boy, have you never taken art class down there?
Okay, our black and white colors.
Yes.
No, it shades of
I know. Black is all but white is also all
No, black
Ever
is,
think about
black
that?
is
Okay,
You
guys.
know, you know what?
Flanges.
I don't wanna
Everybody got the
hear
flanges
it.
and stuff?
Yes.
Is everybody not talking and listening to me?
Put the flange.
No, the answer is no.
Everybody's not.
Okay, so we're gonna click this edge and this edge and that edge.
Those are some edges.
Let's hear you.
Just click some edges.
Oh man, I didn't even click
Just
that.
any old edge.
Any old edge will work.
I have to restart.
Alright, so let's do some settings here. So the length of the flange is gonna be measured from this back surface to the edge of the flange, which is this option, bend from the intersection of the two outer faces. Okay? The flanges are gonna be flush with the end of the rectangle that we just created. So you see how these are flush? That's what we want. That's this setting here. Excuse me. The dimension from here to the end of the flange is going to be 0.875. Basically, the reason for that is we want this to be an inch overall when we nest the two together. We want it to be an inch overall, but we need to have some clearance for the inside radius of the other part, right? Because they're going to be bends, so we got to make sure we clear the bend radius on the other part, so we don't want to make the flange the full width. The bend radius is going to be 0.039. Which is 1 millimeter, roughly. In addition to that, go to corner, and under relief shape, pick tear. And click OK.
What do you mean? You did the wrong thing.
You guys got that?
What did I do?
Well, look at mine and look at yours.
What's the difference?
It holds
It's
like
like mine. Never mind. Yours is flipped around.
Yeah, okay, mine's fine.
What was the? Change that to 10.
Alright,
Can you do the corner thing again?
I look at gray.
And that needs to be.
corner, drop down list, tear.
0.039 or something like that.
0.039.
No, what exactly
Don't
does that
I
little
don't know.
blue circle where in that
Okay.
drop down?
Orion.
Tear and stuff.
Orion.
What is that blue circle represent?
Like this.
Yeah.
So basically, alright, well if I do
Not
this,
listening to the strangler.
it actually, it's gonna be more obvious if I do a larger bend radius, if I do like a 1/8" bend radius. It's hard to tell on this thin material, but on thicker materials it's more obvious. So you see how there's like this kind of like square notch here? If I do tear, like that. If I do,
I saw the bend
round,
Why is it being?
why is it it's supposed to be round?
Yeah, that's what it was.
Like that. Laser well.
Where is it?
That. So basically the idea is just
0.1.
tear.
Let's go back.
Tear is the simplest when you create your flat pattern. That's all.
Orion.
Josh,
Maybe I'm just a
dang it.
Orion. I need help. What was the bed radius?
0.039.
I told you.
This is actually what I wanted. So when I told you guys to pick tear, don't pick tear. Tear doesn't do what I want it to do. Pick linear weld. Go back, edit your flange,